do one. All right, so you've heard the word optimize before, right? Optimize, if you're trying to optimize something, what does that usually involve or entail? Make it better, right? More efficient. There you go. You're making it better for sure, possibly, but there is some kind of like a constraint or there's some limiting factor, right? And that's why we use the word efficiency. Efficiency implies getting the most for the least, right? Getting the most for the least. So that's kind of what this is here. When we're trying to optimize something, we're trying to get the biggest possible outcome possibly, or sometimes we're trying to get the smallest possible outcome. So anytime you hear the superlative case, right? EST, biggest, smartest, ugliest, sleepiest, whatever, we're talking about extreme values, right? And that's all optimization is. Optimization is basically finding absolute, which we also called global, which we didn't even have to qualify, max and mins. Or I should say max or mins, okay? We already know how to do that, right? We already know how to do that. The EVT says if a function is continuous on a closed interval, it's guaranteed to have both a max and a min, right? And they can occur at what two values possibly? The absolute extrema. Where? They could be endpoints, right? Team endpoint, right? This is the game again where they're all sitting at the buzzers. Team endpoint or team on the interior team critical values, right? Yeah. So in other words, local max or mins could be absolute max or mins on the interior, but it could be an endpoint. Now, some of the times we're going to have endpoints, and it's up to us to define the endpoints because optimization is going to end up involving it's where math and English collide. These are word problems. And so we're applying it to real life phenomena. So when you apply a mathematical model to a real life situation, you have to come up with a relevant domain. Not all the values that work for the math equation are gonna be relevant in the real world, right? Like when you talk about exponential growth with something, exponential functions have domains of all real numbers. But in reality, when you're applying it to like the population of wolves growing in a forest, that's not going to apply from negative infinity to infinity, right? So we come up with a relevant domain. And on that relevant domain, we can possibly establish endpoints. And when we can do that, it's going to be easy to find the absolute max or absolute min, right? Because all we have to do is find the endpoints with the relevant domain, find any critical values on the interior, and then test the values by plugging them into our function. And the biggest is the biggest, and the smallest is the smallest. And we've solved life's pressing problems. And we get Nobel Prizes for it, possibly. Nobel Prizes. Oh, I'm sorry. We get no Nobel Prizes. I didn't say enough no's, right? We don't get Nobel Prizes. We get no Nobel Prizes. Well, we enjoy doing it at least, right?
We do.
We certainly do. All right. I like the new environment, the new atmosphere. You are very respectful, and I appreciate it. But it is a little quiet. It's kind of like creepy. It's a little creepy. Look, no, please don't. No, please don't. Please don't. It just takes some getting used to, and I can get used to it. Okay, I can get used to it. I can get used to it. Okay.
Actually, what he's saying is 1 or 2 notches maximum going up.
Yeah, maybe volume 2. Yeah, volume 2. Okay.
Out of
10. Out of 10. Yeah, 2 to 10. All right. No, I don't want to lose the sparkle. Okay. Example 1. Let's try it out. Let me show you what I'm talking about here. Okay. This right here is a typical AP question. Like some of my examples in this section get a little bit outlandish because I like this section. But this one here is AP caliber, right? Find 2 positive numbers whose sum is 60. Well, that's easy, right? 59 and 1. What else, right? Oh, wait, no, 30, 32 and 28. All right. But here's the catch, right? Here's the catch. Here's the catch. We want the product of one of them times the square of the other one to be as big as possible, a maximum. Don't get your toga in a knot. Now, let's talk about guess and check. If I come up with a list of addends, that's what they're called, that add together to give you 60, and I multiply one of them times the square of the other, and I find the largest one in my list, is that guaranteed to be the largest one in existence? Bigger list. What if I make a bigger list then, and then I find the largest one in that bigger list? Is that guaranteed to be? No, because there's infinitely many possibilities. It didn't say find two positive integers, right? If it said find two positive integers, now it's a finite list. But we're talking about numbers. So it could be like 59.1763277, right? And then the other number. Whoa. So yeah, we don't want to create an infinite list and then find the largest one in there because first of all, it's impossible. And therefore, no expansive list, regardless of how expansive it is going to be complete, right? And the biggest one in your list may not be the biggest one, right? So we're going to do it a little bit more, what's the word, efficiently, right? We're going to use math. So first of all, when you read a problem like this, how are you going to know that it's optimization? What's the key word? Don't get your toe good enough. Well, I wrote this, I skipped it, but this is what Greek youth did back in the day before TikTok and phones. They challenge each other in the sand and out in the street for these types of problems. What's the word that tells us it's going to be optimization? Maximum, right? We want it to be a maximum. And it doesn't say absolute maximum. It doesn't say global maximum. It doesn't have to. A maximum. All right. So that's the key word to say it's optimization. Now, here's how you're going to do every single optimization problem. You got to squeeze your own juice, right? There's no equation given. You're going to write this first. You're going to write, I call it a primary equation. A primary equation is going to be that to be optimized. That to be optimized. All right. So what are we trying to maximize? We're trying to maximize the product of one number times the other one squared. Okay. So I need to give a name. I get to choose my own variables here. That's what's kind of cool about it. I'm going to let the product of these two numbers be named. I don't know. How about capital P for product? Huh?
Push P, baby.
Yeah. Pushing P, not pushing poop, right?
Right.
This is the good stuff.
Great stuff.
What do you want to call the two numbers? A and B, X and Y, Delta and Omicron? How about X and Y? I'll use X and Y. Okay. Omicron looks too much like a 0. So I'm going to use X and Y. Now, one of them times the square of the other. Okay, there you go. Does it matter which one I square? No, I could do X squared Y or XY squared. It doesn't matter. At this point, you're bringing in your own variables, and there you go. Now, what we're going to eventually do is take the derivative of that, find the critical values, and look to see which one has the biggest product, right, of those candidates. But the problem is, this is a product now in terms of two variables, X and Y. I have a single function P in terms of two variables, X and Y. I need it to be a function of either X or Y, not both. So we're going to need a secondary equation. Secondary, that's how I'm going to spell it, equation, okay? Or an auxiliary equation, if you want. I'll just call it auxiliary equation. How about that? Aux equation. That's a little bit faster. Okay. Now, your auxiliary equation is always going to involve the constraint. Right? We're trying to be efficient here. There is some catch, right? I can't just pick too many random numbers and say 100 times 70 million squared. Oh, that's a big product. What's the catch? Oh, dude, they have to add up to what? 60. Okay. So my two numbers, X plus Y, have to equal 60. There's always a catch. All right. So that's the constraint, right? Your constraint is always going to be a way to relate the two variables that you've already chosen, typically to a number. Okay. Now here's what we're going to do. This is one of the conditions that has to be met, and that's another condition that has to be met. We're going to use the constraint equation to help us put our primary equation in terms of one variable. So it's going to feel a lot like what you did in Algebra 2. Mason's already all over it. We're going to use substitution, okay? We're going to substitute. Now, it doesn't matter which variable we substitute for, but you want to make it easy on yourself, right? It's just as easy to solve for x as it is for y in my secondary auxiliary equation. But think about what we're going to be doing with it. When I plug it in, I can either plug it in for x and have it just be ready to go, or I plug it in for y and then I'll have to square it. Yucky, yucky, gross, gross. Ugh. So I'm going to solve for x. All right. So you do want to give those two things consideration. Which variable is easy to solve for? And then what am I going to be doing with it when I plug it in? So I'm going to solve this for x. So x equals 60 minus y. Now this equation is the one I would box. You don't really need to box this one. It is the auxiliary equation, but this one is important because when we find one of the values, this might be one that we have to come back to find the other one. All right. So I'm going to actually unbox the first one. Okay. I want that one to stand out. Now I'm going to substitute in. Okay. Boom. So now we get P equals X, which is 60 minus Y times Y squared. And hooray, hooray, we have our product in terms of a single variable, which is what we want. Now is the time that you get it in terms of a single variable. Now is the time that you think of a relevant domain. I'm just going to put, should I annotate this? This is substitute. Substitute. Okay. And now we want to come up with a relevant domain. Once you get it in terms of a single variable, you want a relevant domain. So let's think about it. What types of values can y take on? Well, what did it say? It said define two positive numbers. So they have to be positive numbers, right? So y, could it be negative? No. Could it even be 0? No, it has to be greater than 0. And then what is there an upper bound on it? Could it be 1,000? Could it be 61? If it were 61, then the other number would have to be -1, and now it's not positive. So could it be 60? No. If it were 60, the other one would have to be 0. So typically, you can find the interval by letting the other one go to extremes, right? So if one of them is 0, the other one has to be 60. And if one of them is 60, the other one has to be 0. So here's what I know. I know that the winning value has to be some real number between 0 and 60. Now notice that's not a closed interval, but it does give me some boundaries, right? It gives me some boundaries. So I know the number has to be in between there. I know it's in there somewhere. So how do we find it? We find our critical values. So this is basically all of the setup. And that's the only thing that makes it different from what we've been doing. You got to squeeze your own juice. But after that, it's just time to BOTC, okay? Bust out the calculus. So I get to choose which version of the derivative I want. You want to take the derivative using the product rule as is, or do you want to distribute the y squared and use the power rule? Distribute? I probably would choose to distribute as well because it's pretty easy. So P equals 60y squared minus y cubed. Okay, looks good to me. And now we could say either P prime, or you could say P prime of y, or you could say the derivative of P with respect to y. Either one. Okay. Notice that we're not using plain old x and y anymore. We just happen to have a y in there because we chose it, right? But P is for product. All right, now here we go. Real easy. 120y to the first minus 3y squared. Is that ever undefined? Well, not really. It turns out that most of the time we're not even really interested in where the derivative is undefined, because in the real world, when the derivative is undefined, it's most of the time physically impossible, right? That would be like when the farmer's truck is driving infinitely many miles per hour, or he's changing, in a single instant from 70 miles per hour one direction to 70 miles per hour the other. So we typically just set it equal to 0. And that's an important part, right? We're finding critical values. And now, of course, once it's equal to 0, we factor it, right? Look for a common factor. I spy a 3y, and that gives us a 40 minus y. Keep it equal to 0. Once you set it equal to 0, keep it equal to 0. All right, and then all we got to do is set of each equal to 0, which we can state right away, y equals 0 or y equals 40. Now, this is where the relevant domain comes in handy, right? We got two critical values for the cubic polynomial, which has the domain of all real numbers. Are both of these relevant in our example? We know what they mean, but can one of them be 0? No, one of them can't be 0. So there's only one critical value left in our relevant domain, and it's 40. Okay. So guess what? If there is an answer and there's no endpoints and there's only one critical value in the relevant interval, that's going to be bing bong the winner. Okay. Okay. So that's going to be the one we want. That's it. So I'll come back to justifying it later, because a lot of the times you don't have to justify. But if you do, now it's a free response, and that's a different monster. If this shows up as a multiple choice, though, you're like, hey, one critical value in a relevant interval, that's going to be the one we want. So now it's said to what? We answer the question. This is the most important thing. We answer the frickin', I like that word, frickin' question. And here's why it's so important. There are going to be typically lots of things associated with that optimal value. Do you want the smaller of the two numbers? Did it ask for the larger of the two numbers? Did it ask for both numbers? Did it ask for the actual product of one times the other? Did it ask for the difference of the big one minus the small one, right? There are so many things it can ask you related to that optimal value. So now we need to kind of circle back and say, now what was it that we were asking? Find the two positive numbers. Okay. So now that I found y, and again, if you want to box him, we typically don't need to box our answers. But if you want to box him, that's fine. How am I going to find the other fellow now? Yeah, you plug it back into your auxiliary equation, right? So I'm going to start a new column. And again, signal your intention. I'm going to say when y equals 40, colon, right? You get x equals 60 minus 40, which equals 20. Okay. Now, if I bring the x down there and I box it up, is that enough to walk away on a free response? Did that answer the question? I found the two numbers. There they are. Right. And the reader's like, where are they? There's lots of stuff. Where are they? They're put them in the same box. Well, there's another box. No, we found the two numbers. It's 40 and 20. We write a sentence. Thank you, Lauren. Right. I'll use friggin this time. Write a friggin sentence. Okay. So these are instructions. I'll put them in asterisk, right? Okay. And then again, a good transitional word to tell you that you're shifting gears is so the two numbers are. Now, should I just say 20 and 40? Or does it really matter? Should I keep the labels attached to them that I put? I don't? Well, if I don't put the labels, just a question, how would I know as an idiot which one to square? It's the product of one of them times the other one squared. If you just give me the two numbers, I don't know which one to square. Just keep your labels attached to them. Yeah. So the two numbers are x equals 20 and y equals 40. Now, when you keep the labels attached to them, and we look way back over here at your original equation, we're like, y is the one that you're squaring. And y happens to be the bigger one, which, that makes sense. Okay. So it turns out that the answers were two really nice integers, but that's not always the case. All right. So they may have shown up on your list and they may have had the largest product on your list, but you still wouldn't be 100% sure that there weren't others out there that weren't on your list that were actually a bigger product. But the calculus told us otherwise. Okay. That's an optimization problem. It's kind of fun, right? It's not that bad. Yeah, it is a puzzle. And you get to squeeze your own juice. Now, let's talk about the justification. Okay. We can't use the EVT here, can we? Because we don't have a closed interval. We have a relevant domain from 0 to 60, but we can't include 0 and 60. So how in the heck are we going to justify if it's not a closed interval and we can't use the EVT? Well, there's two ways. There can be a modified first derivative argument or a modified second derivative argument. Okay, so remember those two arguments were without modifications. They were arguments for local or relative extrema. Since f prime changes from positive to negative at this point, that means immediately to the left and right. You can turn a local argument into a global argument on an interval by saying not only is f prime, positive immediately to the left and negative immediately to the right, but you could say f prime is positive everywhere to the left on our relevant domain, and f prime is negative everywhere to the right on our relevant domain. And when you say everywhere on your relevant domain, you're saying then essentially that f has to increase everywhere to the left and decrease everywhere to the right on our relevant domain. And therefore, it's not just a local max, it's an absolute or global max on our relevant domain. Okay, that's why the relevant domain is so important. So let's see if we could do that. Let's set up a quick number line chart. Okay, we'll call this our modified first derivative test, FDT. Okay, we've got x and we've got p prime. I'm sorry, we had y. My bad. Just using y, x, and f prime again. So we got y and p prime. Make a number line chart. And of course, we had the number 40, right? But here's the deal. We have to keep it in our relevant domain. So this was 0, which was also a critical value. And there was 60 over here, which was not a critical value. Well, let's pick a number like, let's pick 30 and 50, right? Now, when I plug it in, I'm going to plug it into which version of the first derivative? Full-fledged factored version, which is right here, right? So we plug into 30 and we get a positive times a positive. And that's positive, right? And notice, since 0 is a critical value, it's not only positive immediately to the left of 40, it's positive everywhere from 0 to 40, okay? And then I pick a number to the right of 40, like 50, and I plug it in, and I get positive times negative, which is negative. Now we're saying that not only is p prime negative immediately to the right of 40, but really, since 60 is not a critical value, p prime is negative everywhere to the right of 40, right? Forever and ever and ever and ever. So now all we have to do, the chart gives us no credit. So now all we have to do is, if we had to justify, you could say y equals 40 maximizes p, and it's kind of nice to throw this word in here, absolutely, because it has a double connotation, right? For us, when we say absolutely, we mean the terminology absolute max, but it also kind of has that je ne sais quoi in the English language, right? It maximizes p without a doubt, right? Absolutely. Okay. Absolutely, right? Don't use that. And then you would say because, and here's the phrasing, because p prime is greater than 0 for all y on the interval from 0 to 40, and p prime is less than 0 for all y on the interval from 40 to 60. Boom. Okay. So no, and you can phrase it differently too. You could say P has an absolute max at Y equals 40 because that's how we did it with the local max and min. P has an absolute max or a max or a global max at Y equals 40 because. Now, notice that this, if you read it and understand it, it has a global flare to it rather than a local flare, right? Y'all know what the upside down capital A is, right? It means for all. So not for one. P prime is greater than 0 for all Y on this interval, everywhere to the left on our relevant domain, and P prime is less than 0 everywhere to the right on a relevant domain. Therefore, P has an absolute max at Y equals 40. So you could phrase this first part, differently. You can put it after it, but this is the new part. This is the global part. And what makes it global rather than local? It's the for all, right? That makes it a global argument. You're not just saying immediately to the left and immediately to the right. Okay, so that's not that much of a modification, right? If you had to justify, a lot of times you don't even have to. But now we've convinced ourselves of two things. First of all, that Y equals 40 was the value that did indeed give us an absolute maximum product and not an absolute minimum product. Oh, that would have been embarrassing if it gave us the absolute minimum, right? Then we would shout out the answer at the top of our voice, and we would actually be the opposite of winners. We would be whatever Charlie Sheen is not. Is Charlie Sheen still winning? I think. Is that a thing still? No? Okay. And the second thing we're sure of, there used to be a phrase back in the day, like before y'all were born, Charlie Sheen is winning because he was always in trouble with the law. But never mind. I don't want to. I mean, it's like pop culture history. It was like a meme before memes were memes. And the second thing it tells us is that without a doubt, indubitably, absolutely, there's not another number out there that's going to give us a bigger product. Okay. So when you use it like this, it's almost just kind of like recreational math. It's kind of fun. You challenge your bros to some kind of challenge like this, and then you find the answer. But it has a lot of applications in the real world. In economics, and in engineering, you're trying to find, the maximum allowable weight limit on an elevator, right? Yeah, I don't want that thing to break, right? You're trying to maximize your profit. You're trying to minimize your costs, whatever. It's good. It's good. Okay. If you understand that one problem and everything involved, you understand optimization because that's all it is. The only difference is the scenarios, the situations tend to vary. Okay. All right. Questions on that one? Did you look up Charlie Sheen is winning? Did you look it up? Yeah. Is he still winning? Oh, okay. So y'all were born at least. Yeah. But y'all are younger. Okay. Charlie Sheen. Okay. It's kind of crazy how time accelerates when you get older, right? If you looked at the time on the x-axis and how time feels on the y-axis, it would be increasing concave up. The weight, the relative, like it's like the wind chill factor, but for aging, right? I'm actually 47, but I still feel like I'm 20, because I don't know what happened in the last 20 years. They went by so fast.
Reports say that Charlie Sheen might be winning after 2018. He decided to get sober.
Oh, there he is.
Yeah.
Okay. Sweet.
He's gonna try and win again.
All right. I'm gonna skip example 2 if you don't mind. It's basically maximizing a pipe cleaner. You take an 8-inch long pipe cleaner and you're gonna use it to bend it into 2 shapes. Yeah. Oh, look. Yeah. We maybe do this as a calculus lab after the AP exam where I give you actual pipe cleaners and you can make ninjas out of them. Huh? I don't know. I don't know how they do that. Okay. Let's look at example 3. This is where it gets fun. A ladybug farmer. Now, someone a couple years ago said, "Sir, I think you mean rancher." And I'm like, make your own damn problem. Okay. It's mine. A ladybug farmer has 500 inches of fencing that he wants to fence off in a field to make a rectangular pen. Now, The field borders on a straight river. Okay, so he wants to enclose a rectangular grazing area for his ladybugs. But here's the thing, he doesn't need fencing along the river because ladybugs can't swim. And I know what you're thinking, well, they can just fly over the fence. The ladybug farmer has clipped their wings. It's a painless process. It doesn't, the ladybugs don't mind. Yeah. Was there?
Like chicken.
So here's the deal. What are the dimensions of the fenced field that will give the largest grazing area? Okay, for his ladybugs. Now, most people talk about like building a fence in feet and they're using it to, you know, fence off dogs or cattle, but not me. Okay. So 500 inches of fencing instead of 500 feet. He has this on hand already. He bought it a long time ago at the Ladybug Farming Store, and which is next door to the Ladybug Ranching Store. Don't get them confused. And he bought a roll of fencing. It's probably about an inch tall, but it's a roll of 500 linear feet when he rolls it out. Okay. Linear inches. Yeah, that's what I meant. So let's go ahead and draw a picture. On the first problem, we really didn't need to draw a picture. But if it involves geometry, and a lot of these will involve geometric formulas or geometric shapes, draw a picture, right? So there is the river, and I know what you're thinking. Is it below that or above that? So I'm going to have my river be up here, and then I'll make the grazing area down below. So here's the green grass, and what he's going to do is this. He's going to fence off. So it's going to come out, it's going to go across, and it's going to come out like that. And then his ladybugs are going to be all in here grazing. Okay. Now, two things. He doesn't want to have to buy any more fence. He wants to use every single inch of his fence. He's not going to be wasting it. So you can imagine that he's just bending the corners and it's running out to completion. But he wants it to be as big as possible in there because these ladybugs are hungry. So first of all, how do you know it's an optimization question? What's the key word? Yeah, it doesn't say biggest, but it has a word that means biggest, right? Largest, right? There's the superlative case, EST. He wants the largest what? Area. So we're trying to maximize, you want to write this? We're trying to maximize area. We didn't write that on the last one that we were maximizing profit or sorry, product, but here we're trying to maximize area. So let's go ahead and write our area formula. What letter do you want to use for area? A is a good one if you're not using it to store values on your calculator. And for a rectangle, it's just length times width. So here's where you get to define your variables. Do you want to use L and W? Do you want to use X and Y, A and B? L and B? You use L and B. That's going to confuse me. I'm going to use L and dub. Yeah. Okay. Now here's the cool thing. On your diagram, label what L and W are. Your diagram helps frame the problem for you, and really it helps define your variables. So now over here, the area is going to be L times dub. All right. Now that's the one I want to maximize. That's what I want to take the derivative of, but I have the area now as a function of two variables, and that is no good. So I need my auxiliary equation that involves the constraint, or constraint equation, auxiliary equation, secondary equation. I'm just going to write constraint over here. And what is, or equation 2. What's the constraint? What's the deal? What gives? It's usually going to involve a number, right?
500 inches.
He's got 500 linear inches of fencing when he rolls it out. So what has to equal 500? Well, come over here.
Length times 2 width.
Length times 2 width?
That's what I meant.
Yeah, he's going to roll out the width. He's going to turn the corner with no waste. He's going to have length all the way here. He's going to turn the corner and come back here. And yeah, that's another W. So W plus L plus W. Is everyone okay with that? W, let's walk around the perimeter. L plus W. I'm sorry, W plus L. Well, y'all are smart enough. Y'all can connect. W plus L plus W. My W's are funky. There we go. Or if we simplify it, 2W plus L. Now, this what makes it a little bit different. If he was framing it all the way around, all four sides, then it would be 2W plus 2L. It would be the total perimeter. And most people have an intuitive sense for what those dimensions are. What do you think the most optimal rectangle would be? And when I say optimal, I mean a trade-off, largest area per perimeter, smallest perimeter, a square. Nature loves symmetry. So regular polygons are very, very beautiful. They occur in nature. So a square would be the answer. So this one has a slight variation to throw it off from being square. You don't need fencing along the river. All right. So now, which variable you want to solve for, W or L? It's easier to solve for L, no doubt, but look what we're going to have to do with it. When I plug it in over here, that's okay. It's just as easy to plug in for L or W, right? So let's go ahead and solve this guy for L. L is going to equal 500 minus 2W, and I'm going to box that one because I might need to come back to it. But for now, I'm going to substitute it in. So I get the area is L, which is 500 minus 2W times W. Once you get it in terms of a single variable, that's where you come up with a relevant domain. So what types of value can W take on? Well, what's the smallest W can be? The smallest. Yeah. No. It could be a half. Or another, what's the lower bound? 0. There you go. Now, instead of doing it as an inequality like I did last time, you could do it as an interval. Now, can W actually be 0? No, because when W is 0, all he's doing is he's rolling out the fence completely along the shoreline. And that doesn't enclose anything, okay? Yeah. What's the largest W can be? 500 is a nice upper bound. That would work, but look what W is. I'd have to go out and come straight back. So W is going to be a maximum when L is a minimum. We can use 500, but I think we could shave off a little bit. 250, right? Because he's going to go straight out, perpendicular to the river, bend the fencing in half, and come straight back. But what that's going to do is it's not going to enclose anything at all. So one can argue that we can put brackets around the 0 and 250. And when we did, those two extreme values would not give us a maximum area. In fact, they would give us a what? A minimum area, because the area would be 0. When W is 0, there is no area because it just runs along the river. And when L is 0 and W is a max, it's just like a piece of fencing that comes straight off the river that's double thick. It encloses nothing. So those are both going to be 0. And therefore, by the EVT, it would have to live on the interior. Well, for us, those geometric values don't make sense, but I do know that somewhere in between, we're going to have positive area, right? I know for sure there's positive areas in the middle or in between somewhere, and that's going to have to be the answer, right? So let's find it. We now need to take the derivative of A with respect to W. Do you want to do anything first? Distribute? Yeah, let's distribute. So A is 500 W minus 2W squared. Now let's take the derivative. A prime or A prime of W or dA dW is 500 minus 4W. Notice the calculus part is not that hard. That was it right there. We BOTC'd right there. Simple little two-term power rule, right? Not that difficult. The setup and the drawing, that was the fun part, right? That's never undefined. And by the way, again, we're not going to be looking for the undefined values here because the ladybugs don't like them. It doesn't make sense in the real world, but it's never undefined. So now we have a linear equation. We solve it algebraically, and we get W equals 500 divided by 4, which is what? 125? And it's my final answer. I should probably put units. I didn't have units on the first problem, but what are the units here? Inches. Okay. Now, that is the only critical value that we get on our relevant domain. It's going to be the answer we want, but we don't just box that and walk away, because now's the part where you excuse my language, We answer the freaking question. We answer the freaking question. Did it want the side length perpendicular to the river? Did it want the side length parallel to the river? Did it want the actual area of the region? Did it want the names of the ladybugs, right? That's not related. So now we come back up. What did it ask us for? What are the dimensions of the field? Oh, okay. Do you think we should tie the dimension, the labels to the dimensions when we answer the question, Ellen? Yeah. So let's come over here. So if you want to put this word in there, so the optimal, you don't have to do that. Dimensions, you don't have to say of the field, are, and then we'll put W equals 125 inches. And I guess L has to be 125 as well, right? Because it's square, right? No, not necessarily. We never found it. Let's circle back real quick before we answer the question. And again, we'll say when W equals 125, we get L equals 500, sorry, minus 2 times 125 is 250. And so we get L equals 250 feet. Yeah, thank you. It's an old habit, right? When I build stuff around the house, it's always in feet. Now we got inches. W equals 125 inches. Or you could say by if you want. That's usually like 2 by 4. And L is 250 inches. And now we know which one's which. We know that W is the length perpendicular to the river, and we know that L is the side that's parallel to the river. So we answered the question. Did it turn out that this thing ended up being a square? No, not at all. Okay. It is a true, it's a true rectangle, right? It's actually longer L than it is wide. All right. And there you go. Now, what if it asked to justify? Okay, this is the optional part. What if it did ask us to justify? You could use a modified first derivative test. That's fine. Just like we did. But sometimes a modified second derivative test works nicely. So just to review the second derivative test over here, the second derivative test, right? If you plug in your critical value and get a positive number, it's a local max. And if you plug in your critical value into the second derivative and you get a negative number, it's a, I'm sorry, local min. My brain, local min. And if you plug in your critical value and get a negative, it's a local max. So the nice thing about it is, again, it doesn't require information on either side. This works especially well when you have a table of values, okay? This works nicely here. Now, the bad part about the second derivative, again, is you actually need the second derivative. We don't have the second derivative. We did find the first derivative, which is here, right? And that's not even the factored version, but how easy is it to get the second derivative? Come on. Oh, it's very easy. So let's just do that over here. We're going to put a double prime is, what is it? -4. Holy crap. There's no variable anymore. That means that our area function is concave down where?
On all.
On all.
The whole thing.
On all the whole thing. Everywhere, right? For all values of W. For all real numbers, including on our relevant domain, right? So that should not be surprising to you, because look at the equation. Our area equation was a quadratic with a negative leading coefficient. It's just a parabola that opens down. In fact, if you were to graph the area against the width, what happens when W is 0? Plug it into the area equation right above the factor version. When W is 0, you get 0, right? And what happens when W is 120? What happens when W is, what did we say the Vegas could be? 250? 250 times 2, it's 0, right? So here's 250. And the parabola does this. Now the rest of the parabola goes on like this, right? So yeah, not only is our value of 125 the midpoint of the x-intercepts, not only is it a local max, It's the absolute max, right? So when you have a parabola that opens down, that's pretty cool. So here's what we're going to say. Justify. A double prime is less than 4, which is less than 0 for all W on the open interval from 0 to 250 inches. Again, you want to make it specifically for your argument. Do you even have to say anything about concavity for the second derivative justification? No. You just have to say what the sign of the second derivative is. If you want to put in there like, therefore the graph of A is concave down, that's just a lot more writing. So this is the modified justification. And what makes it global? For all, right? And you're giving an interval, okay? So we'll word it the way we did previously. So A has a max at X equal, oops, I need to change this one more time, at 125 inches. I did a double prime and I didn't plug in a number. Is that okay? Yeah, W, thank you. Yeah, I was trying to keep that the whole time. We really should, a double prime is -4 everywhere. It really is. But really, again, speaking to the theorem, we should probably say a double prime of what? Yeah, W, which is 125. Yeah. So that's being very specific for our argument. Now, in a case like this, where we're actually not lying, it is actually concave down everywhere. They might overlook it, but you don't want to rely on exceptions and their good nature, because it is pretty systematic. Although it is a very subjective thing to grade, they try to objectify it as much as possible, right? They try to make it so that everyone's grading it the same way. And then there's people outside the grading convention center with signs saying, do not objectify calculus. Don't objectify calculus. Calculus is not an object, right? Yeah. Anyway, that was my attempt at a bad joke. All right. So we did 2 examples today, but in each example, we summarized pretty much the entire philosophy of optimization problems. And you saw the 2 ways that we ever will be justifying if we ever have to, right? There you go. And a lot of the time, most of the time, actually, we do get to draw a picture. So fun. Yes. All right. We'll finish this tomorrow and be working on this worksheet, but not the one that's on the internet. I'm going to work on that today and I'll have it posted in Canvas. Right now, you're focusing on 3.5, okay, which is due Monday. All right. Y'all have a good lunch.
I'm like, all right, that sounds awesome. And then we didn't write a